Jiabin Jia, and from the Institute for Digital Communications, and I teach electrical and electronic engine discipline, second year and third year courses. I can recognize some of my students here. And today my talk and the title is Seeing Through Agile Tomography. After my talk, hopefully you can see through the tricks of the Agile Tomography. Yeah. Actually, Agile Tomography can help the industry or doctor to see through an opaque process. Normally, we can't see it from the outside surface. So first of all, a mini English lesson, and sounds very ironic with my dodgy English. I'm giving an English course here. So what is the tomography? Maybe it's your first time to hear this word, but definitely actually you heard it before, but in a short version, like CT in the hospital. T is from the first letter tomography. C is a computed tomography. So basically, the similar principle, like the patient just stand there and read your source and sight and the light to you, and the camera on the back accept the image. And then the radio source will move to the next position, next, now take a rotation. Alternatively, the patient can rotate really fast, but it must be very dizzy and not a pleasant process. So imagine rotating, and the sight and the light, and something on the operator is picking up the signal. Exactly in the principle. So non-intrusive, because you can't feel any painful or you can't feel any pain, and it is an imaging measurement technology, can provide a cross-sectional image, or also can be 3D one, like from the top up to the bottom, like a 3D image. So tomography is a word derived from the ancient Greek, means a slice of image, cross-sectional image. And agile tomography, that is the keyword in my talk. Agile means like flexible or low cost. Also, like in the city, in the hospital, you have to go to the hospital, stop your normal work, and stand there. It's not real you. But with an agile tomography, you don't need to go to the hospital, and the machine will go to you. You can do whatever you normally do, or in the pilot plant, the chemistry reaction can happen there. So I just put the sensor there, and the measurement is in situ. Emphasis in the in situ measurement. Don't disturb the measurement or the reaction. So that is the process tomography family. Some famous siblings, X-ray, optical one, and gamma ray, also the scary ones. And today I'm talking about another two nice brothers and sisters, like the electrical method or electrical tomography and acoustic tomography. Two error bars, so compared to their advantage and disadvantage. In a space scale, this group, it can provide really accurate resolution. Normally, it's the 1% of the diameter of your chest, or even lower. But for this group, the resolution is low. The image is not that sharp, not that clear. But the advantage is really fast, much faster. Because X-ray or gamma ray takes a few seconds or a few minutes to provide one image. But for this group, 1 second can provide you more than 1,000 frames. So it can catch really fast reaction. So the first one, electrical impedance tomography. So the principle is you stick the electrodes on top of the head or on the chest or on the boundary of the pipe, and the machine inside So inject the current to an electrode or measure the voltage on the electrode, and then rotate. Again, rotation, again and again. So some simple equation that is voltage on the boundary, that's a constant map S, it's constant. And the conductivity, that is the image inside. To solve an inverse problem, just put this S on another side to take an inverse. Sounds really simple, but it involves really advanced math knowledges. Because the main audience here is an undergraduate student. I would say in my research, so which course you will be using, including my courses. And math, first of all, really important, first year, second year. And we design a machine, so electronics, analog circuit, digital circuit, every knowledge you learn from undergraduate course can help you to do research. I designed the hardware board. There are single pieces on the board. The student will put use the soldering gun to put the components on. But that is the easy bit. Difficult part is design the circuit. FPGA, any third year student or second year student, you will be learning FPGA. Programming, second year course, my course, engineering software tool. Learning the programming even with one language, but same principle, you can use different language to program, or you can learn using the same skill to learn different languages. That is some basic specifications of electrical impedance tomography. And really fast provide a 3D, 2D image. Because it's fast, so the information extracted from the machine can be fed back to the control loop. The main applications, medical one and the industry measurement. So in my talk, mainly is some case study or examples of the applications here. So also the CO2 absorption and calibration with measure that. So that is an example, and the sensor was made by Gordon. And the measurement process is you will take the reference one, like there's two pencils. You don't put the pencils in and take the measurement once, and then put the pencil object in, it tells you image. This one is a metal bar, so different color to tell you different conductivity, which one is more conductive than another. And that is 3D image, real-time image, or you can replay back again and again. So the previous one is a single frequency, excitation frequency is only one, but we have to take a reference. But the reference is really difficult to take. Like today's U is totally different with yesterday's U. But yesterday you're not in hospital, today unfortunately is in, but there is no reference. Also for the industry process, we can't ask the manager to stop to create a reference situation for my test. Not really expensive sometimes to shut down and change the flow inside. So if we use a frequency difference like this one, it's a banana or the screwdriver. So we don't need to measure the water only, just use different frequency to get an image. Because the screwdriver is non-conductive, has no reaction with frequency, but the banana is some cells, membrane. It has a capacitance component there. It has reaction with no frequency. That's the knowledge of first year electrical engineering. And the medical application, that is a brain imaging, that shows that after stimulation, the change in the brain in terms of conductivity. So, like the test unit sitting there, and someone to pull a party pop, and then the brain has a reaction. Somewhere has more blood, somewhere has less blood, because blood is more conductive than normal tissues. And this bit is breathe in and out. When air is in, blue, and when you press out, so it's red. It helps to control the ventilator for the patient. There's real products already there. And exactly the same principle, but I'm confident I can provide similar like equipment. And that is example, like when you drop ink into the water, that is the diffusion process, because ink has, particularly and the salt in the ink. Again, that is the carbon capture experiment, or part of experiment. So if it's only a bubble column, so the gas is more likely distributed on the center of the column. But if I add some packing inside, so the bubble will go around the boundary. Because we are doing carbon capture, we want to find the CO2. First thing is we need to find where is the CO2. Yeah? In that case, the CO2 is on the boundary. So since we can locate where is the CO2, so we can capture it. Yeah? So my technique is to provide the measurement, like the first step to find the CO2. Yeah, that is a very good example. Yeah. The capacitor one, so that is the twins with the impedance one. The previous one measured the wet stuff, anything conductive, yeah, our body liquid. But this one measures dry stuff, like the solid particles, the similar principle. And in that video, the solid particles inside, you can see in the real time to tell you so where is the particle. Yeah. That is the software interface. So everything designed in our university, we own, we completely own the intellectual property. And the example is like this silo, there's a particle inside. Sometimes when you pour the particle inside, you will never get it out because the particles, they gang up together. So that silo is wasted. So with this technology, can monitoring or could tell you what factor affect the dynamics of the particles inside the silo. Either it's in the shape of the particle, temperature, or humidity. Yeah. That is simulation, and that is the measurement one. That is the side view of the discharge process. Yeah. This one is a experiment in the pilot plant in Glasgow. That is oil phase, two-phase flow. Because oil, now the price is low, but it's still valuable. We need to count, we need help to the oil supplier to count how much oil is extracted from the tank. Because if the measurement is not accurate, they will lose the profit. Yeah. And that is, again, the real-time image. Because normally the pipe is a metal. You can't see through the liquid. But with this one, you can clearly see what's happening inside. So oil and water, blue and the black, when they mix together, they will, in this middle point, they will change. Yeah. On one side, so the water is dominating, another side is oil dominating. And at some point, so it suddenly changes to who is an individual and who is wrapping whom. Yeah. So the dry stuff or the easy capacitors one to take the permittivity. When the oil is dominating, so mainly the liquid is non-conductive. So look after this side. But if the impedance one will help to find the information on that side, yeah, conductive side. Ideally, I can measure the whole range from zero, full oil, full water. Yeah. That is a measurement or compare with the real result provided by the pilot plant. Yeah. Now also, the technology can tell you the velocity distribution, or since it provides image, so we can find out the flow pattern. Yeah. At any single moment, so what's happening inside. Acoustic one, that is my new research. So one of PhD students starting working on this new member, like the middle one in the tomography family. So because the sound or ultrasound will propagate with different speed. If the temperature is low or high, speed is different. If for example, this one, that is burner, I put an acoustic sensor around the flame to test the temperature distribution of that flame. Yeah. Also, my vision is to test the water current, like ocean current, because when water is moving faster, it will help in the propagation of an acoustic. Yeah. When water is moving on opposite way, so the propagation speed of acoustic signal is slower. They use this difference to find out the 3D distribution of the ocean current. Yeah. Also, in the Agile Tomography group, I have two more colleagues, like Hugh and Nick. Hugh is specialized on chemical spatial tomography. He used laser absorption spectroscopic to detect the engine, yeah, the combustion inside the engine, or the flight engine, to find out the efficiency of combustion or distribution of the CO or hydrogen or the chemicals. And another colleague, Nick, is specialized in mathematical. Yeah, he's a mathematician. Yeah, he can understand really complicated equations which I never can understand. Yeah, one sentence conclusion. Hopefully now you see through tomography, because tomography can help you to see through an opaque process. Yeah. And thank all my collaborators, my students, my sponsors, particularly thank to Gordon, and he helped me a lot to making this small gadget or equipment. Thank you, everybody. Thank you, the audience.
This production is brought to you by the University of Edinburgh.